Hey everybody, it's Friday, October 9th. Hopefully the test went okay for you guys yesterday. I apologize about the disaster we had with it in the morning, but as I think I mentioned, most of the tests, basically every single other one, is going to be on AP Classroom for the rest of the year. So hopefully, now that we've gotten that over with, we can just go ahead and put it behind us. Um, as you can see here, for today, we have sort of a light day because I put out a question yesterday on Google Classroom. The question was, did you get to collect all of the data for the experiment? And a lot of people indicated that they did not get to collect all the data for the experiment. And so I'm going to give you some time to do that today. Basically, we're going to keep this video short. And since there's no homework to review, if you have any other data to collect for that experiment, then you can just go ahead and get on that right after this. And again, that paper, the Google Doc with the summary of all of your data, is going to be due on Tuesday. Remember, we have off on Monday. Okay, so here, we're really just going to summarize a lot of what we said about one-dimensional motion. And the reason why is because the next topic that we're going to start is free fall. And in general, what I had planned for today was to wrap up regular old one-dimensional motion and then jump right into free fall. And it's perfectly okay based on how quickly we've been moving along so far for us to save some of that stuff until Tuesday. And so Tuesday's video will be entirely about free fall and acceleration due to gravity. And you may remember when we were talking about free fall, acceleration due to gravity, objects thrown straight up in the air. In honors physics, what we saw is that the sign that we use for various quantities is actually really, really, really important. And so part of what we're going to do today is look at some problems which will basically just test / reinforce your understanding of sign conventions. And so if you go to the Google Classroom page, you will see a PDF, which is called Position, Velocity, Acceleration, Sign Convention. I'd like you to go ahead and open that up, and we're going to start here with the first one on this sheet, which is B1QRT47. And on this problem, we see it says 8 possible combinations for the signs for the instantaneous position, velocity, and acceleration of an object moving in one dimension are given in the table. Above the table is a coordinate axis that shows the origin, marked 0, and that indicates that the positive direction is to the right. Notice there you're showing that arrow moving to the right. It says the 3 columns on the right-hand side of the table are to describe the location of the object either left or right of the origin, the direction of the velocity of the object either toward or away from the origin, and what is happening to the speed of the object, either speeding up or slowing down at the given instant. It says the appropriate descriptions for the first case are shown. So they are giving you a little bit of information here about this first case. And so notice it says here the position, the velocity, and the acceleration are all positive. And so the first thing we want to mention here is that, and I don't know how they put this sheet out with this error on it, but whoever proofread this book made a mistake, because when positions are positive, the object begins to the right of the origin. And so essentially what they're saying here is not that complicated. They're saying that position is positive, so it's going to be somewhere over here. And the velocity is positive, meaning the velocity vector is headed to the right. And notice, because it's headed to the right and the origin is over here, that's how we end up with the answer that the object is moving away from the origin. And for the rate, which notice here essentially is the acceleration, is it speeding up or slowing down, they have speeding up because notice we have a positive velocity and a positive acceleration. So what I'd like you to do here is pause this video and go through the rest of this chart, basically filling in the positions, the directions and the rates for these examples shown here, these seven more examples. So notice underneath that, we have this part that says explain your reasoning. This part of this thing I think is really important. Filling out this chart is really not that hard. I think you'll be able to do it pretty quickly. But the explanation part is key. And what I actually really want to challenge you to do is I want you to try to explain all of the entries in this chart using 3 sentences only. This is something that we're actually going to focus in on a lot this year. If you remember, maybe a week and a half ago, something like that, I gave you an assignment on Google Classroom where I basically had you do one of these sheets and answer a question about graphical translations. And on that sheet for graphical translations, you had to draw the graph and explain your reasoning. And some of you wrote just essays about this one little question. And I know a lot of you think more is more, and in most cases, more is more. But in these cases, with these explanations, you really have to start to get comfortable with the idea that less is more. Because if you are just stating the principle with no extra fluff or frills, that's really what we want. We want to get down to brass tacks here, so to speak. And so I think a good thing for you to consider as we continue to write these explanations for the year is, how can I say this as clearly as possible with as few words as possible without leaving off anything that's really important? To be clear, this takes time. It's something that you're literally going to practice for the next 8 months. But it's something that's important nonetheless, and so I want you to keep that in mind. All right, take a couple of minutes to pause this video here. Go ahead, fill out this chart, try to summarize the answers, and when you hit play, we'll go over it. Okay, let's go over this. As we said here, remember, this first one was right. And so we can go through these one by one. There's a number of ways to do this, however you want, or I guess however you wanted was however you did it, but I'm going to go through these row by row. So here, the first one is asking us for the position. Whether it's left or right of the origin is based on the sign of the position, and so that would be right, because the position is positive. And if it's to the right of the origin, and with the positive velocity, it's moving away from the origin as well. And now here, notice the key difference between this case and the last case is that the acceleration is negative, and so this object here is slowing down. So notice, essentially, with a positive velocity and a positive position, there are really only 2 possibilities for the motion. It's either speeding up or slowing down, and that, of course, depends on the acceleration, whether the acceleration is the same sign or the opposite sign of the velocity. Okay. In part C, we see the position is positive over here, and so that means the object starts to the right of the origin. And notice here the velocity is negative. And so I'm going to put this up here. I guess I'll erase it afterwards so it doesn't get too crowded. If the object starts to the right of the origin and its velocity is negative, meaning its velocity vector is pointing left, notice that's actually going to be going toward the origin. And lastly, because now the velocity is negative and the acceleration is positive, they have the opposite sign. So this thing is slowing down. Moving on to D. D has a positive position again. That's our last positive position, notice. So it's to the right of the origin. The velocity is negative, so that means it's going to the left, which means at that exact moment it's moving toward the origin. The only difference here, of course, is that because the sign of the acceleration is also negative, that means the object is speeding up. Okay, and so now we can start to fill this in a little faster, that hopefully we've seen some patterns. Notice all of these positions here are negative for E through H. So I'm just going to go ahead and fill these in right off the bat, right? And I'm assuming that's probably what some of you did. You just said, oh, all those first four positions are positive, these last four are negative, so I'm just going to fill this in straight away. Okay. Now we go to the velocity. The first two are positive and the second two are negative. And so if the position is negative, meaning the object is starting off over here to the left of the origin, and its velocity is positive, it's actually moving toward the origin. And that's true in both of these cases. And notice, conversely, if the object starts to the left of the origin and its velocity is negative, like it's showing in G and H, that means it's moving to the left. And so in those cases, it's moving away from the origin. And now all we have to do is fill in the information about the acceleration. And so here we have the same sign in E for the velocity and the acceleration. They're both positive, and so that would mean this thing is speeding up. In F, the velocity is positive and the acceleration is negative. So this object is slowing down. In G, we have a negative velocity with a positive acceleration, so opposite signs again. And so this thing is slowing down. And for H, negative velocity, negative acceleration. When the velocity and the acceleration are in the same direction, they have the same sign, the object is speeding up. And so notice here, what I've challenged you to do now that we filled in this whole chart is to explain your reasoning to this question using only 3 sentences. And it can be done. How do you explain whether you figure out the object is to the left or right of the origin? Boom, that's 1 sentence. How do you figure out whether this thing is moving toward or away from the origin? You can answer that in 1 sentence as well. And then to finish it off, for the rate, how do you figure out whether the object is speeding up or slowing down? Well, your answer should look a little something like this. And so we can say here the position can be determined by whether the sign is positive or negative, because if it's positive, that means the object is to the right of the origin, and if it's negative, that means it's to the left of the origin. So I'm actually going to go back here, and I'm going to insert a text box because those things are not full sentences. And I'll write here, the sign of the position determines whether the object is to the left or the right of the origin, positive indicating the object is to the right of the origin, and negative indicating the object to the left of the origin. 1 sentence. We've explained the whole position part. For the velocity, I hope everybody knows this. This is super important. The velocity shows you the direction it's moving from. And so it shows you the direction it's moving in, I should say. Let's be careful about that. The velocity shows you the direction the object is moving in. And whether it's moving toward or away from the origin depends on the initial position. So the sign of the velocity shows the direction in which the object is moving, where the initial position determines whether the object is moving toward or away from the origin. And that's a fact, right? We can go through and get into every single possible case, but we don't have to. We can just summarize it nicely like that. And then lastly, for the acceleration, the sign of the acceleration can be compared to the sign of the initial velocity to determine whether the object is speeding up or slowing down. Where a velocity and acceleration in the same direction tells you the object is speeding up, and a velocity and acceleration in the opposite direction tell you the object is slowing down. It took up a little more space than I thought it would. So I'm just going to go ahead and drop that here. All right, so take a second to pause this video and write any part of that down if you want. I hope some of you have some gears turning already in terms of thinking about, like, why are we doing this now, the day before we are going to start to talk about acceleration due to gravity? Because determining the signs of quantities like position, velocity, and acceleration is very important in a free fall problem, because we have a very specific coordinate system we establish for free fall problems. When you hit play, we're going to take a look at the second problem on that sheet. All right, now obviously, to address the elephant in the room, I'm sure some of you are probably thinking it. Isn't it kind of a little insane to try to write that explanation for that question in just 3 sentences? Don't you think maybe 4 or 5 would have worked better so there weren't so many totally long sentences? Yeah, probably. But I hope you all get the point. Trying to really focus the writing is going to be a super important skill, because I know for a fact, because I taught almost all of you before, that a lot of you have the tendency to just say, if I just write as much as I possibly can, perhaps that will get me more points. And that's not necessarily the case, right? You could go through that chart and say, in case B, the position is positive, and so that means the object starts to the right of the origin, and then the velocity is positive, or like, and it could get insanely long. And so the point here is focusing your explanations to just address the key concepts across all of the examples is going to be something you're really going to want to do as we go through this year. So keep that in mind. All right, let's move on to another one. The next one on this sheet is B1 QRT51. And on this problem, and I'm just going to pull it up on the sheet here for a second. On this problem, they tell you the graphs below show the velocity versus time for boats traveling along a straight, narrow channel. The scales on both axes are the same for all of these graphs, and the boats all start at the same origin. In each graph, a point is marked with a dot. Indicate in the chart below, and that would be here, if the position, velocity, and acceleration directions of the boat at the points indicated are in the positive, negative, or no direction. Now, the no direction part seems kind of funny, but notice what's in parentheses there is 0, which should give you a pretty good hint of when that's used, right? All right, take a second to pause this video here, and by a second, I mean like a lot of seconds, maybe 300 seconds, 5 minutes or so, and try to sort your way through this. If I were you, I would start here and work my way that way, because this is the easiest, harder, and then hardest. All right, go ahead. Okay. Now, of course, the obvious question here, I think, is why did I tell you to start with the acceleration? And why did I say that was easiest? And I hope the answer is pretty straightforward. This is a velocity versus time graph. To determine the acceleration, when you're looking at a velocity versus time graph, you'll look at the slope. So the slope tells you the sign of the acceleration. So looking at part A, we can see clearly, looking at that thing, that acceleration is positive. Same for B, because both of them are showing you a graph with a positive slope. Remember, it doesn't actually matter what the velocity is at the indicated point. All that matters is the sign of the slope on the graph. For C, the slope is negative, and for D, the slope is negative. For E, the slope is positive. And for F, the slope is negative. And the reason why I think it's important to just consider the slopes and not really even think or look about anything else is because I think it reveals a very important idea about acceleration. I think what usually messes people up with this is that they think like, well, if the velocity is negative, then the slope, even if the slope is positive, that doesn't necessarily mean that the acceleration is positive, and it does. You have to look at these things dispassionately like that. If the slope is positive, the acceleration is positive, and that's it. It doesn't matter if the velocity is zero, like it is in case A. Whoops, I thought I was on the mouse again. It doesn't matter if it's zero, like it is in case A. It doesn't matter if the velocity is positive, like it is in case B, or if it is negative, like it is in case E. If the slope is positive, the acceleration is positive, and that's all there is to it. Speaking of which, that allows us to look at the velocity column, and I hope everybody realizes here they're giving you a specific point on the velocity versus time graph, and on a velocity versus time graph, the sign of the velocity is determined by, well, it's determined by whether the point is above or below the x-axis. And so for A, that's showing you zero velocity. For B, that's above the axis, so that's positive. For C, that's at the x-axis again, and so that velocity is zero. For D, it's negative. For E, it's negative. And for F, it's above the x-axis, so it's positive. Notice they didn't ask you here necessarily, but you could look and now see if the object is speeding up or slowing down based on the combination of the velocity and the acceleration. Now, this last part about the position is tricky. And if the part of the video when I go through and read the directions is a part that you ignored, then you needed to realize that there's a super important piece of information given in this instruction. And that is that all the boats start at the same origin. Because how can you determine position from a velocity versus time graph? You can't. But you can determine displacement. And if you know the object starts at the origin, then based on the sign of its displacement, you can figure out its final position. And so notice here, at least A is a pretty good example. For A, and I've got this other pen here, but notice for A, the area under the curve gives you the displacement, of course, because this is a velocity versus time graph. And I hope everybody realizes that at that area under the curve right there of that triangle is negative. It's below the x-axis. Here, the area under the curve is above the x-axis, so it's positive. Here, it's above the x-axis, so it's positive. Here, the area under the curve is below the x-axis, so the displacement is negative. Here, also, again, the area under the curve is below the x-axis, so it's negative. And here, the area under the curve is again above the x-axis, so it's positive. Now, let me just be very clear about one point. When I am looking at these graphs and I am looking at that shaded area and trying to figure out whether it's positive or negative, I am not figuring out the sign of the position. I am figuring out the sign of the displacement. But because the objects start at the origin, if the object's displacement is positive, that means its final position is positive. And if it is displaced to the left of the origin, then that means when we look at it, it's going to be left of the origin. And so your answers here, just running through them real fast, are negative for A, positive for B, positive for C, negative for D, negative for E, and positive for F. And that's it for the chart. And so, of course, the big question here is, well, how do we possibly explain it? And we already kind of went through those things, but let's just go ahead and address that real fast. So we'll open up another text box here. And so we can say, well, how did we figure out the sign of the position? Well, the sign of the position ultimately is determined by the sign of the displacement. We can say here for the position, since the objects start at the origin, the sign of the position, let's say final position here too, the sign of the final position is determined by the sign of the displacement, which is determined by the sign of the area under the curve. And you could just write AUC for that if you want. How do we figure out the sign of the velocity? Well, since this is a velocity versus time graph, sign of the velocity is determined by the y-axis. And lastly here we can say, well, let's say, I'll write this, you don't have to if you don't want to, since this is a velocity versus time graph, the sign of the slope determines the sign of the acceleration, since the slope represents the acceleration. This graph. And that's it. It's pretty clear. It's concise. It's pretty hard to misunderstand that. And so that's that. Take a second to write any part of that down if you want to. Go ahead and pause that. And when you hit play, we're just going to talk about one more quick example before we go. Okay, last example here. This may look familiar to you. A couple weeks ago, I posted a sheet for you called Position as a Function of Time worksheet. This question was actually on the back. We never got to it, but I want to talk about it here just to remind you of a couple of these things, particularly because we did an experiment the other day where interpreting a position versus time function proved to be a pretty important skill. So I'd like you to look at this thing right here. And again, we are going to go over this in a minute. I want you to look at this question. It says, describe the motion of an object that is represented by the following equation. And here I want you to violate the rules that I just gave you. I want you to write as much as possible as you can about the motion of this object if that's its position function. Pause this video here, take a couple minutes to do that. When you hit play, we'll go over it. Okay. So hopefully you wrote something decent down for this object. And I think as you'll probably see, there's not a whole lot that we can say about this. So what can we say first? Well, the first thing that we can say here is about the initial position. We can say here, since this object begins with a positive initial position, the object starts its motion to the right of the origin. The initial position is the first term in the position function. I'm going to write in parentheses here, actually, there is not multiplied by any t term. We can also talk about the initial velocity. We can say the initial velocity term is multiplied by the t in the position function. And what we can say is, since the sign of the initial velocity is negative, the object will begin its motion by moving to the left. Since the object has no acceleration, due to the absence of a t² term, this object will move at a constant velocity, negative 2.8 meters per second. There's really only like one more thing we can say here, which goes back to the first sheet. Since the position, let's say the initial position, since the initial position is positive and the initial velocity is negative, the object begins by moving towards the origin. Eventually, the object will reach the origin, move past it, and continue indefinitely toward the left. And that is just about as much as you can possibly say about the motion of this object. If you'd like to write any of that down or amend your statement, you can go ahead and pause this video. But with that, that's it for today. This class is usually supposed to be 90 minutes, right? It's a double period. This is the only thing I really want you to do today, besides assembling your data and making your measurements. If you have any questions about that video lab, there are 2 Zoom meetings today. And again, if you're watching this today, today means Friday, October 9th. And you could ask about any questions about that experiment in there. Or you can ask any questions about the experiment through emails or comments. Again, I'm expecting you to submit that assignment by Tuesday at midnight. All right, everybody, have a nice long weekend. I'll be posting another video for you on Tuesday. Take care.